All right, so hello everyone. I'm Norman Wahlberger. Today we're having a little tutorial. We're going to go over some of the problems that I've laid out in this course up till now, and we're going to have a look at some solutions to some of these problems. All right, we'll start with the cissoid problem, where we defined cissoid in terms of a circle and a line. And maybe our coordinates are like this, x and y with 1 up there. And then the idea is that we're going to take a line like this, see where it intersects the circle and this other line, and then we're going to translate this vector down here back to the origin and see what the locus of this point is then, getting something that looks like this. And the problem is to find a rational parameterization of this cissoid. Okay, so let's have a look. How might we proceed? Well, first of all, this equation of the circle is probably going to be important. So the circle has equation, center is at a half here, so x squared plus y minus a half squared equals 1/2 squared, or x squared plus y squared minus y equals 0. And let's have a look at this line that we're using to define the cissoid itself. So let's sort of get some control over that line, maybe by thinking about this parameter here. That's the point, say, whose x-coordinate is t and whose y-coordinate is 1. So let's call this point P and this point Q. So let's let Q be the point T1. And to find P, what are we going to do? Well, we want to write down the equation of this line and then see where it meets the circle. So the line OQ has equation y equals, well, it's got a slope of t, because that's, no it doesn't. It has a slope of 1 over t. So the equation, maybe we should write it as x equals ty. So when y is 1, x is t. We don't always have to write an equation of a line in the form y equals mx plus b. And in fact, generally speaking, the best approach to thinking about a line is to think of it in terms of the form ax plus by plus c equals 0. That's a symmetrical form for a line. So it's a good idea, generally speaking, if you're working with lines, to think about them with that general form rather than y equals mx plus b, because this is more general in particular. When b is 0, this will still make sense, but the other one won't. All right, we've got that line. Then, so it meets, so the line has this equation and meets the circle where when, okay, what's the equation that we need? We need to plug this into the equation of the circle. Here's the equation of the circle, so we'll replace x with ty. So getting t squared y squared plus y squared minus y equals 0. So y equals 0, or well, maybe I'll just factor it. That's the honest thing to do. So y times ty plus y minus 1 equals 0. And therefore we get two possibilities. And so y is equal to 0, or y equals, there's a t squared here, or y equals 1 over 1 plus t squared. All right, if y equals 0, then we're talking about this point here. We already know about that point. This is the point that we're interested in. So its y-coordinate is 1 over 1 plus t squared. And what is its x-coordinate? Well, it has to be given by this. So x equals t over 1 plus t squared. So that's the point P. Maybe we'll write it down here. So x-coordinate is t over 1 plus t squared, and the y-coordinate is 1 over 1 plus t squared. All right, so we have the point P. There's the point P with coordinates we found. So what do we have to do now to get the cissoid? We have to find this vector PQ and translate it to the origin. Basically, we have to find the vector PQ. So let's say, going over here, the vector PQ will be the difference between the q coordinate and the p coordinate. So t comma 1 minus t over 1 plus t squared comma 1 over 1 plus t squared. And then we have to get this over a common denominator. So t minus t over 1 plus t squared, I guess that will be t cubed over 1 plus t squared. And 1 minus 1 over 1 plus t squared, that's going to be t squared over 1 plus t squared. And that's, in fact, then, if we translate it down, well, that will actually be the coordinates of this point right here. Right? So that is a rational parameterization of the cissoid. This is a rational parameterization of the cissoid. X is this and y is this. T is a parameter. All right, there's one more thing that we'd like to do here, which is to find an algebraic equation for the cissoid. So to get that, we want to essentially eliminate the parameter and just get a relation between x and y. So let's do that here too. So to find an algebraic equation, we need to eliminate t from the two equations, x equals t cubed over 1 plus t squared, and y equals t squared over 1 plus t squared. Now this kind of problem is sometimes quite tricky. In this case, it's pretty easy because we actually know that the relationship between x and y is, we know that t can be directly expressed in terms of x and y because that's how we set things up. All right? So we recall that the way we set things up was that t was actually just the ratio of x and y. So that's already t in terms of x and y, which means we can then substitute it into either one of these equations and get an equation that doesn't have any t's anymore. This one's slightly simpler, so sub into y equals t squared, 1 plus t squared. So if I replace t with x over y, I get x squared over y squared, 1 plus x over y squared, for a total of x squared over x squared plus y squared. And then that, if we equate that to y, we get an algebraic equation for the cissoid. So altogether, y times x squared plus y squared equals x squared. That's now an equation just relating x and y. We've eliminated t. Okay, notice the way I've written things out. I've been rather verbose, but maybe not too verbose. I've tried to tell a story. I've tried to write more or less English sentences. Maybe not completely, but I'm sort of aiming to do that. And if I was actually doing this on an assignment for lots of marks, I would make sure that I would try to write English sentences. So I might even have a period, for example, at the end of statements like this, making it look like a work of literature as well as a work of mathematics. All right, good. So that's the first question. The next one I want to look at is a parameterization question. So the next question I want to look at is the question, parameterize the conic x squared minus 4xy minus 2y squared equals 3. It's not necessary, but if you have a computer algebra program around, it's probably not a bad idea to quickly graph this thing and see what it looks like, just out of curiosity. And it's a hyperbola that does something like this, roughly. And we need a point on the hyperbola to start with. So we have to actually just hunt around for some small values of x and y that will satisfy this. Unfortunately, in this case, it's not that hard to do that. So we find by trial and error that the point minus 1, 1 lies on C. Let's call the thing C. All right, so we're going to use that as our base point for a parameterization. And most of you got this fine. There are many possible answers because there's lots of ways of choosing an auxiliary line to set up your parameters. So I'm going to do something just a little bit different, which a few people did. So just to give you an alternate view, which is sort of in keeping with our approach to things, that if you have a problem involving a point and a conic or a curve, if you translate the point to the origin, maybe things are simpler in general. Okay. So let's do that. So let's translate C so that the point, let's call it A here, goes to the origin. Okay, so we get a new equation, x minus 1 squared minus 4x minus 1y plus 1 minus 2y plus 1 squared equals 3. And admittedly, you have to do a little bit of algebra here. So we simplify this to get x squared minus 4xy minus 2y squared minus 6x equals 0. So we really actually translated the conic. I might just sort of try to draw it like this. Yes?
Should it be the other way around? Should it be x plus 1, 1 minus 1? Is that when you go
Well, if you think what happens if you replace x with and y with 0, 0, you're going to get minus 1 squared, minus 4, this point, this point. You're going to get the original points. There's a minus sign here because this is a minus sign. Generally, it's x plus the x coordinate, y plus the y coordinate, to translate it down. Okay, so now that the thing is at the origin, our point, it's the point 0, 0, so the parameterization of the line can be relatively simple. And now we set y equals t times x. In terms of a parameterization, I guess what we can think about that being, well, that's a kind of a slope. There's the line y equals tx. If this is 1 and that's t. So what we're really doing is we're using this line x equals 1 and the natural parameter on it to make lines. All right, we set y equals tx and we sub in. So we get x squared minus 4, plug in y equals tx, so tx squared minus 2t squared x squared minus 6x equals 0. There is a common factor of x, which we'll pull out, and x minus 4tx minus 2t squared x minus 6 equals 0. And this x equals 0 corresponds to the point that we already know, which is on this conic. There's already one point on the conic that we know. There's one solution already that we know. So there's no need to use a quadratic equation. Okay, quite a few people had some equation, but it's going to be quadratic, and then they said, well, we're going to use the quadratic equation. You don't want to do that. You want to observe that there are two solutions and you know one of them already. So in particular, if you have a quadratic equation and you know one solution, then you know what the sum of the two roots are because of the coefficient of x, or you know what the product of the two roots are because of the constant term. All right, so you don't have to use the quadratic equation, you don't have to invoke the square root. All right, so now we've got the condition x equals 0. Or we can solve for x here, or x equals 6 over 1 minus 4t minus 2t squared, in which case y is then given by t times x, so that's relatively simple. So y equals 6t over 1 minus 4t minus 2t squared. That then is a parameterization of this translated red conic. And to get a parameterization of the original one, well, we have to translate that back. So translate back to get parameterization of C, and that will be x and y is equal to, well, in this case, what we do is we can just write 6 over 1 minus 4t minus 2t squared minus 1. And the other one is the y-coordinate, 6t over 1 minus 4t minus 2t squared plus 1. Question?
What's like the domain of T in that parameterization?
All right, so this is a good question. What's the domain of T here? And this is a little bit, it's seemingly a little bit tricky because it looks like there's two branches to this hyperbola. That maybe you need to think about both branches separately. In fact, that's not the case. The algebra takes care of the whole story. There's a slight complication, though, in that you really, to fully understand this parameterization, you really need a projective view. So it's a full parameterization only when you go to the projective view, which allows a point at infinity in this direction. So in the projective view, this line has a point at infinity, as we've learned. Okay? And you should really think of that point at infinity as being an extra point which you need to complete the parameterization. Why do you need that extra point at infinity? Well, because there will be a certain direction to this, to these lines that we're drawing. So we're drawing lines through here, or let's say through here. So most of the lines that we draw through this point will actually meet the conic at some point, some other point. But there's this sort of, there's this one here, which will meet it at this point here. Yeah. And then there's also the line that's parallel to the line that we're using, which will also probably meet the conic somewhere. So this line that's vertical, which is in the same direction really as the parameter line that we're using, should be thought of as meeting this line at infinity. So you're getting the corresponding point on the hyperbola when you set t equal to infinity. What does that mean? Well, it doesn't mean that we need, it's just a projective view. It just means that when t gets large, the denominator here will become large and this whole thing goes to 0. And when t is large here, we get 0 here. So in that case, we're just picking up the original point that we're talking about. So the answer is, it's a good question. the full parameterization is obtained by thinking about the projective view where you have to add a point at infinity to the line. Yeah?
Don't you have to make sure that t is not a root of that quadratic equation in the denominator?
Not really, because, okay, so that's another good question. Okay, what happens if t is a zero of this denominator here? In that case, you would say, well, this blows up. Okay, what does that mean? Well, what that means, and there will typically be two such values of t. So there will be two directions where it seems as if that something strange is happening. To understand that, again, you need to go to the projective point of view. You need to realize that this conic that we're talking about is a hyperbola, and it has 2 points at infinity. Okay, this is a hyperbola, so it has asymptotes. So it has 2 asymptotes like this. And as the conic gets further and further away, it gets closer and closer to these asymptotes. And where those asymptotes meet the line at infinity, that will be a point that actually the conic goes through. And there will be 2 such points, one for each asymptote. So in other words, the full conic is not just the conic you see in the plane, it also has these 2 points at infinity, and those are exactly the points that you're picking up when you're looking at the zeros here. When you get the 0 down here, then you're essentially picking up those points at infinity. And if we use projective coordinates instead of affine coordinates, that would all be completely clear. You know, if we, instead of using capital X and capital Y, if we use little x, little y, little z, the 3 coordinates, 3 homogeneous coordinates, then that would be completely clear. We would see that, those points at infinity being parameterized this way. All right, so let's now go to one of the more challenging questions that I've given you so far, which is find the evolute of the power function y equals a times x to the n. All right, so we'll do a quick diagram. Function, typically something like this. And of course, the parameterization is easy enough to cook up. We can say let that be t, and then that will be the point t, comma, a t to the n. So what we'd like to do is we'd like to find, in terms of t, where the associated center of curvature is. That's the center of the osculating circle that best approximates the curve at that point. Or, it's another way of thinking about it, it's the place where adjacent normals meet. From the 17th century point of view, adjacent normals meaning just 2 normals which are very close to each other. They're sort of limiting position as the 2 points get together. All right, so our strategy is going to be to compute these normals, compute the intersection of 2 nearby normals, and see what the limiting value for this point is. All right, so the first thing that we do is, well, we've said that already, but let's write it down. So parameterize the curve by t, a, t to the n. So at this point, what we'd like to do is write down the equation for the normal. The simplest thing to find out is the derivative, because we know how to differentiate it very quickly. And the derivative is giving us the slope of the tangent. Okay, so if we differentiate y prime equals n a x to the n minus 1, that's the derivative. And so at t, the slope of the tangent is n a t to the n minus 1. That's the slope. And so a direction vector for the tangent so a direction vector is, think of that 1 and the slope. Then a direction vector is 1 comma s. Say v equals 1 comma the slope, n-a t to the n minus 1. That's that vector there that I'm drawing, v. So that's a vector in the direction of the tangent, which is of course perpendicular to the normal. And that's the best thing that you want in order to write down the equation of the normal, because you want to write down a line in terms of its normal. So the normal has equation, or the normal is, well, we're just going to take this vector and take the dot product with x and y. So 1 dot x is x, plus this dot y is n-a t to the n minus 1 y. And that's got to be equal to something. And what's it got to be equal? Well, it's got to be a line that goes through the point that we're talking about. So this point has to satisfy the equation of the line. If we plug in x equals t and y equals a to the t to the n, we're going to get what it has to be equal to. So it has to be equal to t plus, I have to replace y with a times t to the n, so that'll be n-a squared t to the 2n minus 1. All right, or sometimes, we like to write it with everything on one side. We can do that too. Minus t minus n-a squared t to the n minus 1 equals 0. That's an equation of the normal at the point t. So similarly, at point u, so another parameter on the curve, let's say u here, so that'll be u and a u to the n. Similarly at u, the normal is, it's exactly the same thing with t's replaced with u's. So x plus n-a t to the n minus 1, no, I said t replaced with u. So u to the n minus 1 times y minus u minus n-a squared u to n minus 1 equals 0. So we have two normals. What we're going to do is we're going to find the common point of intersection and then let u approach t. And see where that common point of intersection drifts towards. All right, so how do we solve the intersection of these two lines? Well, we just have to, these are just two linear equations. We have to solve for x and y, two equations in x and y we have to solve. Okay, it's probably simplest just to subtract these equations because there's an x here and an x here. So if we subtract, the x will be gone immediately and we'll just have a single equation in y. That's very simple. So I'll leave them there and go up here. All right, so solving. Well, what's the best? Okay, I'll just take the difference. How's that? Okay, I'll take equation 1, equation 2. So I'll take equation 1 minus equation 2. What's that do for us? So the x's will cancel. We'll have an n. Well, we'll have y times n-a t to the n minus 1 on this side and minus n-a u to the n minus 1 on that side. And then probably we should bring everything else to the other side. So equals, so if we bring this stuff here on the other side, we'll have a t, and then there'll be a u, and so it'll be t minus u. And then we have this n-a squared t, so plus n-a squared t to the 2n minus 1. And then there'll be a minus, similarly, n-a squared u 2 to the n minus 1. So I guess we can just solve for y by just dividing by this. So y equals, and we'll try to factor things. So there's a t minus u, and then there's an na squared times t to the 2n minus 1 minus u to the 2n minus 1. Divided by the coefficient of y here. There's an na that's a common factor, and there's a t to the n minus 1 minus u to the n minus 1. All right, so it's easy to make a little mistake, so let's just check that we haven't done that. Okay, it's very good to go slowly and to check that you've done every step right, because you make a little mistake, then you mess up your entire calculation, and then you have to find it later, and it causes you all kinds of extra work. So have we done that right? So we've taken this equation minus this equation, the x's have canceled, this minus this gave us that, and then we took this to the other side, and we had to subtract this to the other side. So t minus u, and this was with a plus sign, and then this one with a minus sign. And then we took a factor of na squared out of there, and we had a t to the 2n minus 1 minus u to the 2n minus 1. And down here we factored na, t to the n minus 1, u to the n minus 1. Okay, that looks about reasonable. All right, now we have to ask what happens as u approaches t. Well, obviously there's a bit of a problem because everything goes to 0. This goes to 0, that goes to 0, that goes to 0. Now, if you have done calculus, you know that this is not such a problem. There's something called L'Hopital's rule, and we could differentiate things appropriately and get some kind of limit. But it's also useful to think a little bit more elementarily and say, well, how could we do this if we didn't know calculus and L'Hopital's rule? Well, what we notice is there's a factor of t minus u here, and there's really factors of t minus u here and here. The problem of this everything going to 0 is because of these factors of t minus u that are actually around. So why don't we just identify what those factors are and then cancel them at the top and the bottom and get rid of them. That requires us to know that this thing factors as t minus u times something else. So we need an algebraic identity. We need to know that, let me just say it a little bit more generally, that t to the, say, k minus u to the k equals t minus u times something. It factors. And this is the kind of thing that should be known by all undergraduates, but perhaps isn't. It is? Good. I'm glad to hear that. Okay, so how do we extract the factor? Well, we just sort of do it term by term. We need a t to the k here, so this had better be t to the k minus 1. And then the next one's going to be plus t to the k minus 2 times u. And then we keep on going. The powers of t decrease, the powers of u increase, until the second last one will be t times u to the k minus 2. And the very last one will be u to the k minus 1. This is not really such an unfamiliar formula. It's really just the geometric series formula in disguise. Okay, if you think what happens if, say, t equals 1. If t equals 1, this is just the geometric series formula. All right, it's really the formula 1 minus u to the k over 1 minus u equals 1 plus u squared all the way up to u to the k minus 1. And conversely, if you remember this one and you want this one, it's just a question of replacing u with a over b or L over m or something like that, and then you can extract that one. Okay, so that's good. So one more thing to remark here. How many terms are there here? So there's if we're thinking about powers of u, we're going from u to the 0 all the way up to u to the k minus 1. So there are altogether k terms. That's going to be important for us in a second. All right, do we buy that? All right, so now having that at our disposal, we can replace this thing with something like this. We can replace the thing down here with something like this. And then there'll be this common factor of t minus u everywhere that we can just drop. before we take the limit. That'll make it much easier to take the limit. All right, so let's do that. So let's just rewrite this thing. And I'm going to cancel that t minus u that's going to appear everywhere. So I'm going to have on the top 1 plus na squared. Now instead of this thing, I had to replace it with something like this. But I have to remember that the power here is 2n minus 1. So I have to write the appropriate series here. So I have to start with t to the 2n minus 2. And decrease in powers of t, 2n minus 1 times u. And then they go all the way up to the last one, u to the 2n minus 2. And on the bottom, we had n times a. Same kind of story. Down here? Oh, thank you. Yes, 2n minus 2. That's right. This should be 2n minus 3. The powers of t are going down, and the powers of u are going up. Thanks. Okay, we're doing the same kind of thing over here, same expression. Now we're starting with n minus 1 instead of k. So the first term that we'll get will be n minus 1 minus 1, which I guess is n minus 2. And then the t's go down, t to the n minus 3 and times u, and the u's go up until finally we get u to the n minus 2. All right, now we can let t approach u. And we can say what we get. So now the limit, therefore the limit of y as, say, u approaches t, we'll do everything in terms of t. What's going to happen? So we're just going to set all the u's equal to t's. So we get 1 plus na squared. What's going to happen here? All these terms are going to be exactly the same. They're all going to be t to the 2n minus 2, because we're setting u equal to t. So the only question is, how many of them are there? Okay, and we said that there is sort of one more than the first power here. Right, if it starts with k minus 1, then they're all together k terms. So they're all together here 2n minus 1 terms. So we have to factor 2n minus 1 here, and each of the terms is actually t to the 2n minus 2. It's in the numerator. And the denominator is so similar kind of story. N times a. How many terms do we have here? So we have to take this first thing and add 1. So there's n minus 2 here, so we have to add 1 to that. So n minus 1. N minus 1 there. And the common terms are all t to the n minus 2. All right, that's what y is. That's an expression for y in terms of t. It also involves a, of course, and it also involves n. Okay, so what do we need more? Well, we still need x, of course. And how are we going to get x? Well, we had a relation between x and y because they lie on these tangent lines, on these normal lines. So I've rubbed it off, but we can perhaps resuscitate it. What was the relation? So one of the normals, I guess the first one was x plus NAT to the n minus 1 times y equals t plus NA squared t to the 2n minus 1. So therefore, if we know x, if we know y, we know x. We can solve for x. We'll take x equals t t plus na squared t to the 2n minus 1 minus na t to the n minus 1 times this value of y. And that is 1 plus na squared times 2n minus 1 t to the 2n minus 2 all over na n minus 1 t to the n minus 2. And again, we better check that we haven't made a transcribing error. I guess that looks right. I've copied y there, and here I've just copied na t squared t then and subtracted na t to the n minus 1. All right. So we have to simplify this, of course. There'll be a bit of cancellation here because there's an na, there's a power of t. So we'll get t plus na squared t to the 2n minus 1. We're going to remember that this is y, all right? This is y here. I'm going to rub all this out to give us some space. Okay, we have repeated that. Now I have to subtract. Na cancels. The t to the n minus 1s cancel. There'll be one more up here, so there'll be a t factor left. There'll be an n minus 1 on the bottom, and a 1 plus na squared 2n minus 1 t to the 2n minus 2. Or maybe I could put that all over n minus 1. Okay, so I'm getting t minus t over n minus 1. So the first term. And then there'll be a certain number of, actually 2 to the n minus 1, t to the 2n minus 1 times n times a squared times 1 from here. I'm just taking that factor out. And when I multiply this t here, I'm going to get 2 to the n minus 1. That's the same power of t. There's an n a squared. I'm going to pull that out. I think I have 2n minus 1 left. All divided by n minus 1. Do you buy that? n a squared t to the 2n minus 1. I've multiplied the t times that 1 already and brought that out. Now it's just t times this, so the 2 to the n minus t to the 2n minus 1 is exactly the same thing as this one here. Okay, looks reasonable. Okay, so what is this now? This here is n minus 1 minus 1, so that's n minus 2 all over n minus 1 times t. And this is plus 1 minus 1 is 2 is 0, 2n. There's another n here. 2n squared a squared t to the 2n minus 1 all over n minus 1. No, I made a mistake. What did I make a mistake? When I put everything over the common factor, there was an n minus 1 down here. And there's also a minus sign here, isn't there? Oh my goodness, I'm very important to check things. Don't trust yourself first time around. Third time around, okay. So there's a minus sign that I forgot. What else did I do? When I take everything over a common denominator, there's an n minus 1 that's under here. So I need to multiply this thing by n minus 1 as well. So instead of having a 1 here, there should have been an n minus 1. But with a minus sign, it's actually 1 minus n. Should have been a 1 minus n there. And that means that that 1 and that 1 minus 1 cancel, and the 2n and the minus n just give me a single n. There's no 2 here. And there should be a minus sign. So we have n minus 2 over n minus 1 times t minus n squared a squared t to the 2n minus 1 over n minus 1. And all of that is equal to the x coefficient. So I might put that in a box. And y we already have. I think y was exactly this thing here, so I'll put it over here. y equals 1 plus na squared 2n minus 1 t to the 2n minus 2 all over, that was all y, wasn't it? N times a times n minus 1 t to the n minus 2. All right, something of a heroic calculation. And it's easy, of course, to go wrong. All right, so you have to go slowly, write neatly. Writing neatly is important. Giving yourself lots of room. Be patient. It actually doesn't take that long if you just go systematically, slowly, step by step. All right, that's good. Okay, so maybe next time we'll come back and we'll do some more of these solutions.